Okay, well.
What if you miles?
I was like 5 years ago. Yeah, it was like really. I don't know what it is class. No.
Yeah, it is class. Sorry. Yeah. Gosh, I thought I got 100 for sure. I thought it was challenge. I also have a remember that video about
It's not easy.
it's like a really good one for this diet. It's like my low strength.
In my backpack.
That is also true.
Good morning, guys. We need to quickly pick up where we left off last week on assignment 27. So on 27, we started talking about polar and playing around with some of that. But again, for a lot of students, they end up thinking polar is more difficult than the vectors and parametric stuff. So I am going to follow much more closely with you on this assignment. So in a second, once I think you all have that out, we'll talk about the stuff we talked about last class, and then together we will move forward and practice this worksheet. And then, because we need a very good foundation before we start building upon it. And then with whatever time we have left over, we'll start the second of 3 sections, which is on trying to find area from a polar curve, which isn't, part of it's difficult, but the rest of it's actually very easy. So anyway, so what we talked about last week on 27 was how polar is a different way to plot a point. Again, this is obviously just a quick version, but you're used to plotting points with rectangular coordinate system, which is xy, which obviously tells you how far to go left or right and how far to go up or down before you plot your point. And polar, we like to write points as r comma theta, so it can be the same point, it's just a different way to get there. R is the distance you travel from the origin, and theta is the angle. So basically, if you know how far and what angle to go, you could land on the same point as an xy. This would be r, this would be theta. So theta always starts at positive x-axis, just like all radians do. So converting back and forth between these is one of the first few things we will do. So if you have r, you could change it to rectangular. Well, if you have r and theta, because x is always r cosine theta and y is always r sine theta. This absolutely needs to be memorized well enough that we can plug it in as we need it. And then when we have rectangular, so we have x's and y's, but we want it in polar, we can use these two. Because in polar, you need r and theta. R could be the square root of x squared plus y squared, and theta is the inverse tangent of y over x. So if we have r and theta, we can use these to find x and y. If we have x and y, we can use these to find r and theta. So those are the ways to switch back and forth. So we looked at a couple where r cosine theta is the same as x, r cosine theta is the same as x, r squared is the same as x squared plus y squared. And then number 3 was the only one that took a little bit of work. Multiply both sides by the denominator, distribute your r, and then we saw an r cosine theta, which we substituted with x, and an r sine theta that we substituted with y. But getting everything in terms of x and y is what's called rectangular form. Getting everything in terms of r and theta is polar form. Okay, and then of course in calculus we're going to want to do things like derivatives. So the derivative is going to work out the same as parametric, where we took the derivative of y with respect to the third variable, divided by the derivative of x with respect to the third variable. That's why it's like parametrics, and we're not having to do like quotient rule or something. So if x is r cosine theta and y is r sine theta, the derivative of y, if you look up here, you'd have to do product rule, r prime sine plus r derivative of sine. The derivative of x, if x is r cosine theta, do product rule, derivative of r times cosine left alone, plus r times the derivative of cosine. So that's how we find dy dx. And then the two hardest questions by far, because you can just quickly see how messy they were, they asked us to find the slope of a tangent line in question 4, which was basically find dy dx at theta equals 0. So I did what I just said, basically do the product rule for the derivative of y, divide by the product rule for the derivative of x, plug in 0 for theta. There's 1, 2, 3, 4, 5, 6, 7, 8 places you have to plug in 0 for theta, but really you're just doing the cosine of theta and the sine of theta multiple times. So it's really easy, and in fact on my paper you may have remembered me saying, it's really easy to make a mistake in the derivative or in plugging these in, even though individually those questions shouldn't give you an issue. Okay, and then finally the last thing I tried to get in last time was if we are trying to figure out when there's horizontal and vertical tangent lines, well, horizontal lines are when the slope is 0, so we set the derivative equal to 0, solved and got 4 answers. A line is vertical when its slope is undefined, which is the same as the derivative being division by 0. So I set the denominator equal to 0 and solved and got 3 more answers. But the thing that you need to remember out of this is algebraically I got 4 answers for horizontal tangent line, 3 answers for vertical tangent line, but for these questions you have to have the picture to verify which ones work. There was only 2 that were vertical, and so we had to think about what those angles could be to know to throw out pi over 2. There was 2 answers that were vertical. For horizontal, I can see that there's only 3, so we had to think about which of these 3 were these 3 and which one not to include, which is why I did not include pi over 2. You have to know to take some of those answers out, and the only way to know is to look at the picture and see which ones to keep and use that as a clue to try to figure out which ones you don't keep. Okay, so as a group here, let's start off together. And all right, question 1. Find the corresponding rectangular coordinates for 7, 5 pi over 4. Now again, what this looks like is it basically means you travel a distance of 7 at this angle. So if you know where 5 pi over 4 is, if you went 7 in this direction, that's the point that they're talking about. This is 5 pi over 4. Okay, so we want to come up with the rectangular coordinates. So down here, should x be positive or negative? And what about y? Okay, so I've got some quick information. Obviously that's not enough to know if you did the whole thing right, but if I get a negative for x and a negative for y, that's a good sign. Well, how am I supposed to be able to figure out what x is? Good, so you have to remember that x is always r cosine theta. Plug in r, plug in cosine theta. Got to use unit circle here. This would be negative square root of 2 over 2. Okay, somebody else tell me what was the formula for y? Okay, r sine theta. So in this case, 7 times the sine of 5 pi over 4, which is also negative 7 square root of 2 over 2. Again, this is where I think that the thinking about where this point would land helps you remember that both of these are negative. That might help you catch some of your unit circle mistakes. But otherwise, like, picture is not really necessary. So when r is 7 and the angle is 5 pi over 4, x comma y is negative 7 square root of 2 over 2, comma negative 7 square root of 2 over 2. Okay, you guys okay with where I found that? Okay, the next one I think is going to cause you some issues because I think there's some stuff that you maybe did, especially if you skipped pre-cal, that you may not realize. But number 2 is calculator active. So I want you to try to find a polar point. There's actually 2 of them, but try to find at least one that has this x comma y. This is rectangular, so when x is 4 and y is negative 2, think about how you could solve for r, how could you solve for theta, it's on the front page, and see if you can use a calculator to come up with one of those points. And then I will help you maybe make a correction and help you find the other point also. But I want you to try it on your own first. Now, if you think you got the answer, where you get stuck, move on to questions 3 and 4. Those are significantly easier. So I don't think we even need to talk about those 2 together. We'll skip those as a group and I'll give you some time to do those later. Even better if you can find both points in number 2. Finished or not, let's talk about this question 2 and how you were supposed to get both answers. Again, I think that you guys might have been able to figure out one, but I'm skeptical that you remember something to find the second one. Okay, so if I want polar, I need it to be written as r comma theta. How did you figure out the length of r? Okay, so r squared is always equal to x squared plus y squared. So hopefully you did something like this. 16 plus 4 is 20. I'm just going to leave this the square root of 20. You could break down the square root of 20 into 2 square roots of 5, but I'm just going to leave it the square root of 20. And the other thing I need is theta. So if I have xy, how am I supposed to know theta? Somebody besides Will, who's about to say the answer. Right, so tan theta equals y over x, so theta equals inverse tangent of y over x. Now, this is why it's calculator active. Even though this reduces to -1/2, and -1/2 is a common ratio on the unit circle, it's not a common ratio for tangent, it's a common ratio for sine and cosine. So you would need to make sure your calculator's in radian mode, throw this in your calculator, and you get this. Now, inverse trig functions are mathematically really only defined in radians anyway, which we need to be in radians. So make sure your calculator's in radians, otherwise it's going to throw some other number at you that doesn't mean much. So does that mean that one of the answers was square root of 20 comma -0.464? Why not? What's wrong with this being one of our answers? Exactly. 0 to 2 pi is like 0 to 6.28, right? -0.5-ish is not between 0 and 6.28. You with us there?
Yes.
Okay. Then what am I supposed to do? Think about this. Let me give you a hint. Think about this angle. -0.5 radians. Well, from here to here is pi, which is 3.14. So half a circle is 3.14. So negative is going this direction, and this would be -3.14. So -0.5 is, I don't know, somewhere in here, roughly. Where's another spot that would have the same tangent value? I'm sorry? Well, that would be up here. That doesn't work because sine and cosine are both positive here. So sine divided by cosine would give you something positive, not something negative. Sorry, add 2 pi? So if I add 2 pi, now I'm going to land in the same spot. So in my calculator, plus 2 pi. Now I'm getting 5.820. That's certainly between 0 and 2 pi, so there's one of your answers. That's the one I thought you might be able to figure out. But there's another place. So, put this over here. Okay, where's another place that has this same tangent value?
If you make negative square root of 20 and positive.
And positive what?
Like 464.
No. If you add pi to this, why pi?
Because it will give you the same slope. The tangents.
Right, so if you think about, I have no idea what sine and cosine are here, but this x length and this x length are the same, but one's positive and one's negative. This y length and this y length, they're the same, but one's positive and one's negative. So with tangent values, the trick that I didn't think you would remember, and it seems like there was some hesitation there, is that if you know the tangent at this point, directly across the unit circle has the same tangent value. The signs for sine and cosine switch, but when you're dividing the same two ratios by each other than the signs, then you're going to get the same value. So what we could have done is just add pi to this, and we could have gone square root of 20 in the .678 radians. So that sounds like something that you may need to know. So at the top of your page, you might write something like, I don't know how you want to word it, but tangent values are the same. If this is 1, directly across is 1. If this is negative, or if this is square root of 3, directly across from that is square root of 3. Tangent values directly across from a circle are always equivalent. So if you have 1, you could add pi to that to get another one, or subtract pi, or add 2 pi. Okay, so there's 2 possible answers. But yes, you could have also done, you could have also tried to make r negative. If you'd done that carefully, there's probably a way to do that. Okay, let's see if there's anything else you want to ask about that one. Otherwise, we are going to skip 3 and 4, because those are super quick, especially compared to this one. 2 is the hardest of those 4. That would be the one I would circle and look back at again. I think there's something you need to get out of that. Okay, but skipping ahead to question 5. Again, I'm trying to do a little bit of some variety with you here since polar is so new to you. There's a good chance that you're going to need to ask some of these others as well. But okay, question 5. This one is super important because, again, we may not get through the next handout very much today. But we'll do at least some of it for sure. We'll start on it when we come back from lunch. But the hardest part about the second unit is trying to figure out certain angles, which a lot of times you have to do from a graph. Sometimes the graph is given to you, sometimes the graph is not given to you. So notice, they are wanting us to sketch a polar equation without a calculator. And this is tough. This is where, if you don't be diligent enough, if you don't take my suggestions here, I really think that this is where students last year thought that polar was hard because they didn't put in enough effort here. Okay, so here's my XY plane, or but I want to try to graph r equals 2 cosine 3 theta. Now, by the way, if you remember how we played around with our calculator sum, what did this 3 theta do to the graph? You remember what that did? Okay, so if you know that, that helps a little bit. Remember, if it's an odd number, you get that many petals. If it's an even number, you get twice that many petals. Now, you don't have to know that, but it's certainly going to make our life a little bit easier when we graph this. So what we have to do is we have to try to figure out what the behavior of this polar graph is going to be. And there's no easy way to start this. We really just have to try to make up a table and start plotting some points. And then with enough points, we can figure out what its behavior is going to be. So, same thing that you did in Algebra 1. Before you started graphing, you started making a table, you picked an x value, you plugged it in, you solved for y. You picked a different x value, you plugged it in, you solved for y. You found a different x value, you plugged it in, you solved for y. And then when you plotted all those points and connected them, you had your graph. Now in Algebra 1, it was mostly linear, so it wasn't so bad. But this one probably doesn't behave the way you expect it to. So, let's plug in some easy stuff. Let's plug in 0. So 3 times 0 would be 0. The cosine at 0 is what? Okay, so in this direction, we're going 2 out before we plot our point. So in 0 radians, directly to the right, we're going 2 units to the right. Now, this says only graph 0 to pi, so I'm not going to bother picking anything outside of pi. But I don't know, I could try pi also. I probably shouldn't jump to the end. I probably should do a bunch in between, but it's fine. It doesn't matter what order we pick them in. So if I put pi here, what's the cosine of 3 pi? Times 2 is negative 2. So that means if you were going in the pi radians direction, you need to go negative 2 to plot the point. So positive 2 would be going this way. Negative 2 is going this way. It's the same exact point. We got the same point twice. So we're starting at 0, we're ending at pi, and the point is starting and ending at the same place. So I got to figure out what's going on in between there. So I have no idea. I'm going to just pick something like pi over 2 and see what I get. The cosine at 3 pi over 2 is 0, times 2 would also be 0. So in the pi over 2 direction, when it's trying to go up, it goes 0 distance before you plot that point. 0 distance from the origin. So that's that point. That, I don't know, it's a little helpful, not much. But also, think about this 3. We can make some good educated guesses. Pi over 3 is a good one, because when I multiply that by 3, I just get pi. The cosine of pi is negative 1, times 2 is negative 2. So in the pi over 3 direction, which would be roughly about here, I need to go negative 2. Now negative 2 is not this, because remember at a diagonal, just like Pythagorean theorem, if this is negative 2 and this is negative 2, that doesn't mean the hypotenuse would be negative 2. So it would be this direction, I don't know, roughly about there. Something like that. That's the best I could do. And you can start to see why this can be frustrating, because we have done 4 points and we still don't know hardly anything about what this graph is doing yet. Okay, so let's just keep going. I don't know, let's try 2 pi over 3. I know that's going to be easy, because when I multiply it by 3, it just gives me the cosine of 2 pi, which is 1, times 2 would be 2. So in the 2 pi over 3 direction, which would be roughly about right here, I need to go 2. So I'm guesstimating that to be about that. I'm trying to color coordinate my points also, but I have to reuse some colors, so. I don't know. I haven't tried pi over 4 yet, so I could try that. 3 times pi over 4 is 3 pi over 4. The cosine at 3 pi over 4 is negative square root of 2 over 2. Times that by 2, we get negative square root of 2. Now what is square root of 2 as a decimal? Or what is it close to? Right, it's about 0.7-ish. So in the pi over 4 direction, which would be this way, I need to go negative about 0.7. Now again, this is only a useful point if you know about what that decimal is, because this is no calculator. So about 0.7, I don't know, roughly about that. Okay. Gonna need more points because I can't see what's going on here. So, what would you pick? What's another angle we haven't done yet that's between 0 and pi? Your choice. Pick something. Okay. We didn't do pi over 6 yet? Okay. So 3 times pi over 6 would be pi over 2. The cosine at pi over 2 is 0 times 2 would be 0. So in the pi over 6 direction, oh, now this is actually pretty helpful. And the pi over 6 direction is going 0. The reason this is helpful is because look, at 0 it's 2, and then at pi over, if we put these in order, it's a little easier to see. But the angle that we have done closest to 0 is pi over 6. So what's happening is when theta is 0, it's at 2, and theta is pi over 6, it's at 0. So what's happening is, from this angle 0 to pi over 6, which is right here, in that amount of time, because that's not much. Do you see how I'm talking about 0 to pi over 6? So it's a little angle, so it's turning very quickly. That's kind of hard to see. Then I know it goes through this point. If I think about pi over 6, then the next biggest was pi over 4, so it would hit this point next. And then the next biggest I did was pi over 3, which is this one. And then the next one I did was pi, which was, oh no, that's not the next one. The next biggest would be 2 pi over 3. So this is where I can cheat a little bit and know that knowing that there's 3 petals kind of helps me know that this goes up here, comes back, and at pi, I knew it ended up back here. Now, did you have to know that there was 3 petals? No, but if you didn't, you can see that you probably would have had to try to find a few more points to try to figure out what's going on there. That is not easy at all, but dealing with these angles like this is going to be so important in the next section. So anyway, that's kind of a quick introduction to get us started there. Okay, are you guys okay with that? Do you see any questions you want to ask? Because again, I know this is going to be your struggle quite a bit in this unit. The best advice I can give you, it may not be today that it becomes a problem, but the best advice I can give you is if you've got to figure out some angles and or you have to figure out what's going on with the graph, more points is always better. If you're not sure, plug in more angles, more angles, more angles, more angles, more points, more points, more points. The more you do that, the more confident you're going to be that you are understanding what's going on there. Okay, let's look at one more together, and then I'm going to ask that you guys try a couple of these because these all kind of have the same directions here. Okay, 6 says find the slope of the tangent line at the given value of theta. Okay, well, slope of tangent line is a way to ask for dy dx. And so over here, remember x, well, let's do y first. Y is r sine theta. So r sine theta, I'm just plugging r in. X is always r cosine theta, just plugging r in. And then if I want to know the derivative of dy dx, that's the same as the derivative of y in terms of theta divided by the derivative of x in terms of theta. So for y, I'm just going to pull the 3 out front, and for theta times sine, you have to do product rule. Now this is in terms of theta, so the derivative of theta in terms of theta would just be 1 times sine left alone plus theta left alone times the derivative of sine divided by x prime. Same thing, I'm going to pull the 3 up front and then do product rule with theta sine theta, theta cosine theta. So the derivative of theta would be 1 times cosine theta left alone. And then over here, theta times the derivative of cosine, which would be negative sine theta. And then if you want to know whatever angle, who cares what the angle is, but that's what you're going to plug in at the end. And typically they pick out nice ones where a lot of this is going to go to 0. Pi over 2, sine of pi over 2 is 1, but the cosine of pi over 2 is 0. So we get 3 times 1 plus pi over 2 times 0 divided by 3 times 0 minus pi over 2 times 1. Since this goes to 0 and this goes to 0, we end up with 3 over... Actually, why not just let the 3's cancel too? No point in doing that. 1 over negative pi over 2, which is the same thing as negative 2 over pi. So you have to know what x is in terms of r and theta. You need to know what y is in terms of r and theta, so that you can piece those together, take its derivative, and then you can find the derivative at a specific point. So that is what 7, 8, 9 will be asking you to do. And the next questions are pretty similar, not exactly the same, but pretty similar. So what I'd like you to do before our lunch break here, go back and do questions 3 and 4. Again, those should be super quick and easy, so if they're not super quick and easy, then you might be on the wrong track and ask for help. Number 7 is just like number 6. Maybe a touch messier, but basically same idea. So I'd like you to do at least questions 7, 3, 4, and 7, and then do as much as you have time for. And then when we come back from lunch, we will do the notes part of the next handout, but then we'll spend the rest of class practicing and finishing up this one. Did I have a good lunch? Yeah, it was nice. How was yours? What did you eat? What did you eat?
What's that?
What did you eat?
Nothing. I was throwing a book.
That's not good for you. You need to
I like a
eat.
big dinner.
Yeah, but you need the energy now. Okay, if you guys would get the new handout front and center, please. It will not take us very long to talk about the next section, but I think it will be beneficial for you to see it even without being done in the first section, because it's going to show you what is going to be problematic. Okay, so this handout is about trying to find area from a polar curve. So this, honestly, there's a formula to this, and the formula is pretty easy, and most of these questions are pretty easy with one catch. There's one part that makes all these questions kind of tricky. But the formula I'm about to give to you is based off of a geometry formula that I don't know, most students typically have not heard this one when they did geometry. But a way to find the area of part of a circle, not a whole circle, but just part of it, is you could do 1/2 theta times r squared, where these two sides would be r, and this would be the theta. Well, radius is radius, so I guess if you have one, you have both. So what this radius is, what you need to see, and how this is a little bit, how we're going to use this, is that the radius length changes. Sometimes it's this, sometimes it's a little bit less, it could be a little bit less than that, it could be a little bit less than that. So radius, we're going to say, is a function of theta, and we're going to say theta with the subscript of I. So as I gets bigger, we're talking about the next angle there. And then for the central angle, this is going to change as well. So if we subtract these two angles, so we're going to call one angle beta and one angle alpha. Just like we tend to use theta for an angle, theta is a Greek symbol. Greek symbols are typically for radian measures. So if we take the bigger angle and subtract the smaller angle, beta minus alpha, and divide that by n, that would be like the number of angles. That's going to give us what's called delta theta. So that's the change in theta. And so what you could do with these two things is you could take the area of this little sliver, and then I could get a little bit bigger, and you can get the area of the next sliver, and then the area of the next sliver, and then the area of the next sliver. And if you want this to be perfect, you need to do this an infinite number of times. So area could be found by summing up from I equals 1 to n this formula up here, 1/2 delta theta times the radius squared Now, this just gives us an approximate area. Ideally, we want an infinite number of these things, so we're going to do the limit as n goes to infinity of this big summation thing. 1/2 delta theta times r squared. And you could obviously put those in a different order. But this should kind of look familiar to you. We did something like this in AB, although truthfully just for like, maybe 20-30 minutes. But when you want an infinite number of things, as n goes to infinity, if you want to add them all up, that's what sigma does. And so we're taking this is a form of area. So if I do this an infinite number of times, I don't just get an approximation like this guy, I get an exact area. Now, luckily for us, do you guys remember when we did this last year? What this was trying to help us with? It was what?
Integrals.
Say it again.
Integrals.
Yeah, this is the limit definition of an integral. The integral symbol is a convenient way where we don't have to say this every time. Now, it would be nice for you to do it every time because you'd remember it better. But basically, the formula that we need will be 1/2, same half as up here, integrate from alpha to beta, so from one angle to the next, r squared d theta. So this, more or less, is just trying to show you where this comes from. They're saying, hey, here's a geometry formula you're supposed to know. If we think of it in sections and generalize it, we can think of it this way. And then if we think of an infinite number of them, now it fits the definition of integration. So now we can just use integration. What you're going to see here, though, is these questions are easy in the sense that if you want area of a sector or area of a region like this, you need to know the formula. I will warn you, one of the most commonly forgot things is the half. Just like the area of a triangle, sometimes you guys forget the 1/2 of the base times height. Same thing here, but 99% of your struggle is going to be trying to figure out what the angles are. Knowing the formula, knowing R is usually just given to you. Really the challenge is trying to figure out how big alpha and beta is. So let's look at their couple of quick examples here, and then we will put this aside till next class. But, okay, so find the area bounded by r equals 5 sine theta. Okay, well, I know that I could do this formula up here. Area will be 1/2 integrating from something to something. Oops. R squared d theta. But what am I integrating from and what am I integrating to get this shape? And now notice, and this is why I wanted to make sure we started talking about this today, because I need this to be on your radar so that you can put some effort into this on the first handout. But you look at your picture over here, who knows what the starting angle is and ending angle is? So what you have to do, and again, this is going to be, I really think this is going to be your problem for the next week or two, is you can do whatever you want, but I think the easiest for you is to pick a place to where it starts and ends, and 0 is the origin's a nice place to do that. I mean, I guess in theory you could work with this point, but you're going to have to do even more work to try to figure out that angle and stuff anyway. So what is true about this point that's not only going to be my start but also be where I end? How big is r in that?
0.
Okay, r is 0. So what we could do is we could do like how when we have to make a graph, we could do a table and we could like try plugging in 0. What's the sign of 0? Times 5 is 0. So I don't know, to me this sounds like we might be starting at 0 radians, but then I have to figure out how far do I have to go before I get back to r being 0. And not just anything the first time. I don't want to say that this, this r might be 0 when theta is 27 pi, I don't know, but I need the next time that r is 0. So you could just kind of inch your way there. You could say pi over 2 gives me 5. I don't know. Pi gives me 5 times 0, which is 0. But was there a time before that? Well, the only way to know for sure is to test more stuff. If I assume that this is pi, I might be right and I might be wrong. So sometimes what you want to do is to take a little bit of an algebraic approach. If I chose to start here when r is 0, maybe just set your equation, plug in 0 for r, and again, this doesn't always work, or I would have started with this, but set r equal to 0, and think about when is sine 0? Well, sine is 0 at 0, and where else is sine 0? Pi. So that And then, of course, if it's something you could do by hand, do it by hand. If not, just throw it in the calculator. So I will do that because I don't have that answer ready to go. But 1/2 integrate from alpha to beta all of r squared d theta. 19.635. Now, one question that, well, two things I want to bring up. One question is, you might be thinking, well, why don't we just use this geometry formula? It's so much easier to work with. But you have to realize that when you're talking about that, you're talking about stuff that has like perfect curvature to it to make a perfect circle. In calculus, we deal with stuff that is like this. In fact, this is probably a picture I should have worked with. We deal with stuff that has curvature to it. So if we assume that this is always our radius, that doesn't work. If we assume that this is our radius, that doesn't always work. So when the radius is changing like this, sometimes the radius is alpha, sometimes it's beta, but it's giving us different lengths there. So we can't just use geometry stuff because of the curvature. Secondly, wouldn't there be an easier way to find the answer to this question? How do you normally find the area of this shape? Right, and what is r in this question? How big is r? 2.5. So if I do pi times 2.5 squared, I get 19.635. We didn't have to do calculus on that, but only because that was a perfect circle. Okay, so do the same thing in question 2. Again, find the area of some polar graph. First part's easy. Derek's going to tell us what the formula is because he's not paying attention. Yeah, exactly.
1/2 beta r squared.
1/2.
Is the area. But we use the 1/2 from alpha to beta r squared d theta.
Okay, so like I said in the last question, knowing the formula takes about 2 minutes of real effort. R is going to be given to you, but finding out from what angle to what angle gives us this area. Because if you're not careful, you might just assume 0 to 2 pi. And sure, this might be 0, but we only want it till we get to here. So we got to figure out an angle. We need 2 angles that encompasses this part. And again, we can't just look at that and see. So you've got to pick a spot to start and end with. If possible, try to deal with 0, just because 0 is an easy one. And then again, you could do 2 ways here. You could try to set r equal to 0, and you could solve this. This 2 next to the theta complicates that quite a bit. But that could work. And or you could try to make a table, and you could just try to inch your way to the right angle. So I'm going to guess that probably when theta is 0, r is 0. But I don't know for sure, so I'll plug it in. Okay, so right here. If I plug in 0 for theta, I get 1 minus the cosine of 0, which is 1 minus 1, which is 0. So that's good. So I can start at 0, but now I have to figure out how much of an angle has to go before this and then stop. And again, don't assume that, oh, it's half the graph, so it's half of a turn. It's not necessarily pi. It could be, especially with this 2 next to this theta, 2 pi might be this and a second loop. We might be getting way too much area if we did something like that. So what I would do is I would pick out an angle very close to this, like, I don't know, pi over 4, plug it in, times 2 is pi over 2, cosine of pi over 2 is 0, so this would give me 1. So in the pi over 4 direction, it's going 1. Now here's, I would add this, even though I'm going to ask you to put it in your table down here for our notes. Oops. I'm going to ask that you put it as on your table over here too, as r comma theta. Here is 1 pi over 4. Okay, that is so much information because I just figured out that pi over 4 moves my angle about this much. So if I just do another pi over 4, I don't know, I'm going to estimate that's probably around here-ish. Add another pi over 4, it's going to be here-ish. I've got some idea of the scale of this now. So why don't we try pi over 2 times 2 would be pi. This would be 1 plus 1, which would be 2. So in the pi over 2 direction, it's going 2. So here's 2 pi over 2. Now I think I know. Think about this. If this is 0 and this is pi over 2, and it's that much of a turn, how much of a turn do you think this is going to be? So this is probably going to go to pi. Now again, you could solve this. You just have to remember how to deal with this too. But now I can see pi over 2 looks to be half of what I want. Let me plug in pi to make sure I get back to r equals 0 since that's where I started. 1 minus 1 would be 0. Now that I've figured out the bounds, either A, it's going to be something we can integrate by hand, we can just do that, or you have a calculator and it's just a matter of typing it in. But 99% of my time spent on this question is dealing with and worrying about the angles. R was given to me, the formula stays the formula, 2.356. And that's an area, so the units would be squared if we cared about units. So again, I'm trying to show you two ways. I don't think one way is sufficient. I think sometimes doing this tedious table, carefully, slowly increasing the angles to figure out if I start at 0, how far do I have to go before I'm back here? Or you could have done, you could set r equal to 0 and try to solve this. And you would have gotten something like this, and you would have needed to say that cosine equals 1 at 0 plus anything coterminal to it. So theta comes from integer multiples of pi, like 0 and 1 pi and 2 pi and etc. But if I just went from here to here, I wanted 0 to pi. Okay, so I know I ran that into the ground there, but are you guys okay with how I found those two angles? At least the process? Okay, let's do this again then on question 3. This time they give us the graph and they want us to find the area of this, just this inner loop. So once again, area, polar, 1/2, integrate alpha, beta, r squared d theta. I just did the whole problem except for figuring out the two angles. That's the only real challenge to this. Now, it's a hard challenge though. So I need to figure out, again, once again, I'm going to start and stop at the same place. So the origin's just convenient. You don't really have to do the origin, but I like the origin if possible. The origin is when r is 0. Which is the same as when cosine is negative 1/2. Okay, so that gives me some information. In fact, I think I could probably pick the angles out now. But let's say I'm not feeling real sure. I might do a couple points. When theta is 0, we get 3. So that's actually this point. Again, I think one of the best things you can do for yourself is plot those points, r comma theta, because then if you do a couple, you can kind of see how the angle increases where the new points are coming from. Again, just pick out easy stuff. Maybe pi over 2 would be 1. So in the pi over 2 direction, it's traveling a distance of 1. Okay, so now I've got something to work with. I know this much of a turn, not the distance, but from this angle to this angle went from 0 to pi over 2. So I need something bigger than pi over 2 before I start, but not a lot more, something fairly close to that. So I don't know. What do y'all want to guess? What's something that's slightly bigger than pi over 2? 3 pi over 2? Okay, we could do that. So, wait, what?
Just 2 pi.
Just do pi, okay. So that would be 2 times -1 plus 1, which would be -1. Wait, is that point even on the graph? I'm seeing more no's than yeses, but it is on the graph. It's right there. Look, in the pi direction, which is this way, just like unit circle, you go -1 to plot your point. So in the pi direction, I go to -1. This is the point -1 pi. Remember, r can be negative. That's perfectly fine. All right, well, that's a big hint too, because pi is halfway through this. I wanted the angle right before pi, and then I need the point after pi that gives me that too. So now I've at least figured out it's something between pi over 2 and pi. Pi over 2 is way up here, pi is way down here. It's something in between those. So what is something in between pi over 2 and pi? Okay, we could try 3 pi over 4. Cosine of 3 pi over 4 is negative square root of 2 over 2. So this would be like negative square root of 2 plus 1, which is close to 0, but it's not 0. Maybe we use this as a hint. When is cosine -1/2? Yeah, why don't we try 2 pi over 3. Now this is -1/2 times 2 would be -1 plus 1 would be 0. So I think 2 pi over 3 would be a good one. And then I need another, so if I call this, here's pi over 2, this would be pi over 3, 0 in the 2 pi over 3 direction. But that's just right here, that's my start. 2 pi over 3. Now I've got to figure out how much more do I need to turn to go from 2 pi over 3 to go to pi and keep going. I need to make sure I get all of these angles. 2 pi over 3 is just to start. Pi's not enough because I guessed that one earlier and I can see that's halfway there. But wait, that's a good hint too. If this is 2 pi over 3 and this is pi, Adair, how much difference is there between those angles? What? Yeah, you're the only Adair. If this is 2 pi over 3 and this is pi, how much difference is there here?
1 pi over 3.
Okay, and this looks to be the same amount, so if I add another 1 pi over 3 to pi, we could try 4 pi over 3, and 4 pi over 3 also gives us 0. So, was that the most efficient way to figure out it's 2 pi over 3 to 4 pi over 3? I don't know, maybe. It was pretty tedious to me, but I'm very sure about those angles now. Now it's either something we can do fairly reasonably by hand, or we have a calculator. And we end up with about 0.544 square units. Units are squared because it's an area. So again, it took me 2 seconds to write down the formula. It took me 2 seconds to plug in r. It took me a couple minutes to figure out the angles. The angles we got to slow down and be extra careful on. Okay, anything jumping out at you about that one? Okay, one more, and then we'll be done with this till Wednesday. Okay, find the area of one petal of the rose, r equals 3 cosine 3 theta. Okay, well, all petals have the same amount of area. So you can do whichever one you want to. They're all equal, but you've got 3 to pick from. I think if you watch the review video where somebody else goes over the notes, I think they picked this one. They think it's easier, but I'm actually going to pick this one. And of course it doesn't matter. Whatever one you think's easier would be perfectly fine. So just like the last couple questions, the area is going to be 1/2 integrate from alpha to beta r squared d theta. The only real hassle is figuring out what angle would you start at and end at to get one petal. So notice if I start here, this is when r is 0. You can tell I always like to try to pick that. So you could go up here and try to start this off algebraically, and you could try to solve that and think about what angles make times 3 cosine of that times 3 give you 0, and that's a fine strategy. I might go back to that, but I'm also going to do a few points from a table. So I don't know, 0 is always a nice one to start with. Again, you shouldn't assume that the bottom's always 0. There's no telling, but 0 and so if I plug in 0 here, 3 times the cosine of 0 would be 3. So in the 0 radians direction, it goes out 3 to plot the point. So here's r comma theta. Now to me that's really good news, because that's right there in the middle. So let me try to, if this is where 0 radians is, I want to make a guess about how much I'm turning before I hit this angle. So if this is 0, what do you want to guess for a second angle, hopefully landing here? Okay, we can try pi over 3. Times 3 would be 0, or would be 1. Pi over 3 times 3 would be pi. The cosine of pi is -1. Times 3 is -3. Oh, this is your fault?
No. I was tripping on that.
Or 5 or 6.
Okay, but is this point on the graph? Yes, good. Okay, y'all are seeing it now. If you go in the pi over 3 direction, which is roughly like right here, go in the opposite, because r is negative, 1, 2, 3, they're actually giving us this, r comma theta. Again, I really think that plotting these points like this is going to help you kind of box in and figure out the angles that you need. Pi over 3 was way too much, because 0 to pi over 3 went here and kept going. Well, to me it looks like I really should have probably only done half of that. So my guess, my educated guess, is let's try pi over 6. 3 times pi over 6 would be pi over 2. The cosine of pi over 2 is 0. Times 3 is 0. So pi over 6, this point is 0 pi over 6. Okay, so what? How does that help me? That's my top? Okay, so let's quit at pi over 6. What should we start at? Yeah, exactly. Look at the symmetry here. You got options. If from here to here is pi over 6, then here to here, can't you see that's the same amount of turn? So this would be negative pi over 6. That's fine. Or can't you just say from 0 to pi over 6 would be all of this area? And then what could you do to that to get the whole thing?
Just get rid of that.
Yeah, you could just double it. So you could also do 0 to pi over 6, but times it by 2, which cancels out that. And that would be fine too. There's not one right way. And that's me even telling you to use this pedal. You can use these other pedals. I think the person who did the notes on the video chose this pedal to do because both angles are positive, but both angles don't need to be positive. So anyway, that ends up being 2.356. So basically what I need you to get out of these notes so that we can hopefully hit the ground running with this on Wednesday pretty well is that there's a formula. All of it's pretty straightforward except for the angles, and I showed you a couple strategies on how you can kind of aim for those angles. If you know unit circle is a weakness of yours though, this would be a good time to spend 10-15 minutes of homework to look it over, because if you're missing some of these values, it's really going to confuse you. Okay, I would like to give you the rest of time to work on the other handout though. So again, I kind of like you to be forewarned about this, because on this first handout there was some questions where we had to think about the angles. Number 5 specifically, where we had to think about angles and how to make a graph. I have a couple of these worked out on the website, but not all of them. I have everything up through question 9 worked out. So I don't know, I think last year's group started doing pretty good once they got to that point. But I will follow up and let you guys ask questions. But I need you to try to get some of this done in class. And then I will ask you to try the rest for homework. So let me give you about 5 minutes, and then I will bug you for a question or two. Again, I went back to the 9.8 worksheet. You don't have to do anything else, or I'm sorry, 9.7. We're going back to the 9.7 worksheet. You don't need to do anything else on 9.8 at this time.
Bless you. Bless you. Bless you.
Thank you.
Okay, I said I would try to help out with another question or two, depending on how quick they are, before you guys left. So, is there one that you have found from 9.7 that you would like some help on? Okay, then please, okay, so 9.8, the area bounded by polar curves. Do more of that if you feel like it, but you don't have to worry about that till Wednesday. 9.7, I need you to practice the rest of the questions on here that you didn't get to. So try all of those. Look at the answer key. Make sure you're practicing with your calculator. There's some of these that you have, it'll say verify your answers, but really it's not just checking, it's actually important. And then before I have you turn this in, I will give you a chance to ask a question or two on Wednesday on this before, because I feel like you still might have a couple questions and you may just not have gotten to the questions yet. So Wednesday I'll give you an opportunity to ask a question or two from 9.7, and then I'll have you turn it in, and then we will focus on 9.8 the rest of the class. But for now, I guess if y'all don't have anything jumping out at you, you can start to find a stopping point here. Got about 5 minutes till dismissal. So I do not know. So how do y'all feel about polar so far? Is it as hard as you thought it was going to be from last year's group? Yes? Well, the good news is there's only 3 sections of it, and you guys have seen 2 of the sections already, so.
Is the third one much harder?
Well, the second one is area bounded by a polar curve. The last one is the area bounded by 2 polar curves.
I guess that answers it.
It depends on how hard you think the area ones are.
So,
What's push the back? That's what each beta will just be. Yeah. Okay. And so, then plug it in. Yeah, because then the each is close. Then you get DR. But you can act like these are actually like the DR and DT, you have like that's actually like providing it. Not in this particular case. But like that's why we set up like that.
I don't know. Area bounded by 2 curves sounds tough, but really it's just doing 2 of them and then subtracting usually. Like saying if I know all this area and then I subtract this much, it leaves how much you want. So.
It's just
we did a lot of that last year, kind of. We did a lot of that last year, kind of. Regular groups.
Yeah. So it really just depends on how good you are at finding the area of the first one. Because if you can do it twice and subtract them, you can do it well. It's my picture from National Merit.
See, now I'm scared the actually did put my video.
It would be in here, I think.
Why'd you take that picture of Rio?
I didn't. That's his National Merit picture.
I should have been there.
He came in for a math Olympian club one day,
I was sick, bro. They didn't wait for me.
and about every 5 minutes, I just made him zoom in a little bit more on
It's so good.
No, I actually.
They didn't wait for
I
me.
didn't know you were going to. I think I never knew you were coming back. You know what part of the library? There. Make sure I get my calculator back. As I said, man, take me. Discussion to do, bro. So you're gonna do it all tomorrow, right? You're gonna do everything?
Do what? What, econ? What are you talking about?
I'm talking about this a lot.
You're
gonna help me, Joe. What are you talking about?
Dang, bro, I didn't need you to do that. My charger fell off. Just bite it. Can't get out. Yeah, for safety. I mean, what can you do with it? I would take my charger with it. I'll take it, see if I can fix it. That's crazy. Oh, it was bugging out on his. It was working fine on mine.
Like you want the charges right?
Like it like go like off and on his.
Oh, I see.
No, I had a great recovery then.
Alright.